I welcome you all to the session of hydraulic machines, and today we shall solve a few numerical problems from radial flow and axial flow pumps. And while solving numerical problems of radial and axial flow pumps, we will try to illustrate the concept that we have learned from the previous classes. So, in fact, solving a few numerical problems will help us to understand the fluid dynamics which is there inside a pump, and also will help us to understand the design aspects of the pumping station. So, the first problem that we shall solve in this class is from the radial flow pump. So, it is shown because I have copied this problem from a particular book and it is written the centrifugal pump. So, that is why I did not disturb that word, but as I said I will prefer to say the centrifugal pump as the radial flow pump. So, basically what we can see from the problem statement is a centrifugal pump which runs at 104.3 radian per second. In fact, the revolution per second is given and which is mounted so that its center is 2.4 meter above the water level in the suction sump. So, basically what we will do, we will try to quickly draw the schematic depiction of the pump and pumping station. So, if we consider a pump, say this is a radial flow pump, so this is pump and it is said that it is mounted so that the center of the pump, that is the datum impeller axis, that is what we have discussed many times, is 2.4 meter above the water level in the suction sump. So, you can understand from the problem statement that the pump datum is 2.4 meter above the water level in the sump. So, this is water tank, right. So, as I said that by solving a few numerical problems will help us to understand the flow physics that is there inside, rather the flow dynamics inside a pump, and that too that will help us to also recapitulate what we have learned in the context of pumping system design. So, this is 2.4 meter that is given. One important thing that I would like to tell over here is that we have discussed about two different I can say modes of operation, that is the flooded suction and the negative suction mode of operation. So, in this case you can see the pump axis, rather the center of the pump, that is nothing but the pump datum, is 2.4 meter above the water level. So, this is water level, say the atmospheric pressure is acting on the water surface. Okay. So, if we go to the previous slide again, it delivers water to a point which is 19 meter above the center. So, again if we go to the schematic depiction and it discharges, so pump discharges water which is, so the discharging point is 19 meter above the pump center line or pump axis, right. And for a flow rate of q meter cube per second, the friction loss in the suction pipe is given 68 q square, that we will write. So, if we write that the friction loss in the suction line, so suction side you can see Hs equal to 2.4 meter and HFS that is given 68 q square, right. So, we have learned this from the previous classes, fine. Next is, and that in the delivery pipe is 650 q square meter. Okay. So, if we write the pump delivery side, then HD equal to 19 meter and HFD, that is 650 q square, right. So, we can easily write from the problem statement. Okay. Now, the impeller of the pump is 350 mm diameter and the width of the blade passage at the outlet is 18 millimeter. Okay. So, now if we try to draw the pump impeller, because this is schematic depiction. So, what I will draw now, if we try to draw the pump impeller, so say nothing is mentioned about the blade till now, because we have read the problem till now, and from the statement till now we have read, we did not get any clue about the type of the blades, that whether it is backward, whether they are backward curves or forward curve. Now, so this is basically, you can see that is D2, right. So, now it is also given pump D2 equal to, it is given 350 mm and width of the blade passes at the outlet is 18 mm. So, basically if we try to draw, so this is, that is given 350 mm and B2 equal to 18 mm. So, pump outlet data. Now, we have also seen that the impeller is having, is nothing but hub plus blades, and so this is the width of the impeller. So, you can understand this is, which is B2. So, this is the width of the impeller at the outlet through which water goes out from the pump. So, that is given. Okay. Next is, the blades themselves occupy 5% of the circumference and are backward facing at 35 degree. So, now if we go to the schematic, we have drawn it correctly. If the rotation is in this direction, definitely blades, those we have drawn over here are the backward curve blades. Okay. Now, it is given that the blade occupy, basically I mean the area, if we look at the area at this circumference, we do not get for the water flow. Some part of the area is occupied by the blades. So, basically these are the blades. So, blade occupy 5% of the total circumference, and backward facing blades 35 degree to the tangent. We will draw the velocity diagram, because we have to draw the velocity triangles to solve the problem. At the inlet, flow is radial, that is also given. So, basically no swell at the inlet. So, this line is giving a clue that there is no swell at the inlet, and radial component of velocity remains unchanged through the impeller. So, basically it is also giving a clue that CR1 equal to CR2. So, we will be discussing those part again, assuming that 50% of the velocity head of the water leaving the impeller is converted to the pressure head in the volute. That is again an important statement we need to understand clearly. So, you can understand the objective, I have discussed this part many times, that the objective of having a pump is to develop head. Now, when water is passing through the impeller of a pump, kinetic energy should be converted to the pressure head. Now, a part of the kinetic energy may not be converted when water is leaving from the impeller. So, it is given that 50% of the velocity head of water, because essentially the impeller is rotating, mechanical energy, I mean the what we can see that the mechanical energy will be utilized to increase the stored energy of the fluid in terms of velocity and pressure, that is what we have discussed, right. Now, what we can see that velocity that also will be increased inside the pump, and that velocity head will be converted to the pressure head through the volute casing, that is what we have discussed. Now, it is given that only 50% of the velocity head of the water leaving the impeller is converted to the pressure head, remaining 50% is not getting converted into the pressure head. So, this is the meaning of the statement. And friction and other losses in the pump, velocity head in the suction and delivery pipes and wall strip are negligible. So, it is also an important statement that we do not require to consider friction and other losses in the suction and delivery pipes and wall strip, calculate the rate of flow and the manometric efficiency of the pump. So, that is what we need to calculate, rate of flow and manometric efficiency of the pump. So, we can now go to the slide wherein we have drawn the schematic. So, you can see now first objective should be, can we quickly calculate the amount of head that this pump needs to be developed. So, this pump is installed in a pumping station with the sole objective of developing pressure. So, liquid will be transported from this place to that place, and you can understand that we need to overcome the static height both in the suction and delivery side, right, and that too you also need to have some amount of velocity at the discharging point. So, basically if we do not consider that part for the time being, at least what we can understand from the problem statement is that liquid will be transported from this point to that point, and for that we need to overcome the static height. So, considering those aspects, can we quickly calculate the head that we develop by the pump. So, head to be developed by the pump. So, basically this is H actual. So, if we can easily calculate the H actual, right. So, if we calculate it, you can understand that is we have discussed H s plus H d plus H s f plus H f d, right. That is what we have studied. If we just now put the information from the schematic, so we can easily calculate, that will be 2.4 plus 19 plus 68 q square plus 650 q square. So, this is the actual head the pump will be able to develop, otherwise it will not be able, the pump will not be able to deliver liquid from the suction tank to the delivery tank, fine. Okay. So, next what we can calculate, see it is also given the pump runs at this radian per second. Okay. So, can we quickly calculate what is the velocity, here I can write, rather I can go to the next slide. So, tangential velocity at outlet, u2 equal to we know that is pi d2 n. So, basically we know what is d2, d2 is equal to 350 mm. So, pi and then it is 0.35 into it is given 16.6 revolution per second. So, that is we do not require to convert it. So, it is already given. So, that is into 16.6 meter per second. Okay. So, that is if we calculate it, we will get 18.25 meter per second. So, this is the tangential component of velocity at the pump outlet. Okay. Now, further see, also it is given that the flow velocity, radial component of velocity remains unchanged through the impeller, and it is also given that at the inlet flow is radial. Okay. So, there is no swirl. So, our objective should be to draw the velocity triangles quickly. So, now if we draw the velocity triangle, at least I mean if we go to the next, here we can draw. So, I mean if we take any particular blade and draw it, say and if we take a particular blade, say this blade, I mean this is rotating in this direction. Okay. So, we can draw the velocity triangles if we take only one blade. So, this is C 1 equal to C R 1, this is U 1, this is W 1, right. So, we can write C 1 is equal to C R 1 because at the inlet flow is perfectly radial, no swirl component, C theta 1 equal to 0, and at the outlet so this is W 2, this is U 2 and this is C 2 and this component is C R 2. Okay. So, it is given that C R 1 equal to C R 2, we can write it from the problem statement. We are not going to take these assumptions over here, but it is already given in the problem statement that the flow velocity component, the radial component of velocity remains unchanged. Okay. So, this is important. Now, what is important that it is shown that backward facings at 35 degree to the tangent, that is very important at the outlet, and that is at the outlet. Okay. So, it is given at the circumference. So, if we draw quickly, so basically you can understand with the tangent. So, basically this is 35 degree. So, this is beta 2 and this is also beta 2 and beta 2 equal to 35 degree. Okay. That is also given. So, we can now quickly solve. This is very important to draw the velocity triangles, otherwise this is my suggestion to you all, that when you are trying to solve any problem, the first objective should be to draw the velocity triangles. Okay. So, now if we go to the next slide, next what we can do, we can calculate, see it is given that d2 is given and b2 is also given, d2 given, b2 given. So, we can easily calculate the flow area at the outlet, right, that is nothing but pi d2 into b2, but mind it, pi d2 into b2, that is the overall flow area, but that flow area is not available for the flow because 5% of that particular area is occupied by the blades of the pump. Okay. So, now if we write it, that we know that flow rate cube equal to flow velocity, I am writing, that will help you to understand the problem in a better way, into flow area. So, that is nothing but flow velocity at the outlet, that is CR2 into pi d2 b2. So, that is nothing but q. Okay. So, from this particular expression we can calculate what will be CR2, that is q divided by pi d2 b2. Okay. So, now as I said you that this much flow area, so this this is the total flow area, but this is not available for the flow. So, that is available, which is available, that is 95%. So, we have to multiply that area by with 0.95, right. So, this is the flow area, but that flow area is not available for the flow, 5% of that area is occupied by the blades. So, naturally 95% we are getting for the actual flow, and that is why it is multiplied with 0.95. So, this is 0.95. So, if we calculate it, we will be getting 53.2 cube meter per second. So, we know the flow velocity at the outlet from the data given in the problem statement. Now, see, question is, if we know the CR2, we know U2. So, we know CR2, we know U2. If we draw the velocity triangles again here, so this is CR2, this is beta 2 and this is C theta 2 and this is W theta 2, this is U2. So, and this is C2. So, we know U2, we know C theta 2, we can easily calculate what will be W theta 2. We know U2, we know CR2. What we need to know, because you can understand, we need to calculate the barometric efficiency. We know the actual head that will be developed by the palm. Now, if we try to calculate the manometric efficiency, that is also known as hydraulic efficiency, probably I have discussed this issue. Now, so manometric efficiency or hydraulic efficiency, that is nothing but H actual by H ideal, right. If we try to recall, just for the recapitulation I am telling you that Euler equation is used to calculate the head that will be developed by the palm, but mind it that head is not the actual head, because we have discussed that while driving, rather when we have derived the Euler equation for palms, we did not take the losses due to friction and other minor losses into account. So, naturally the head that will be predicted by the Euler equation is the ideal head, but in reality accounting all the losses, the head that will be supplied by the palm will be definitely less than the ideal head. So, to take that mismatch into account, one efficiency that is called manometric efficiency or hydraulic efficiency is defined. Question is, if we try to calculate the ideal head, we need to apply, rather we need to recall the Euler equation, and that is nothing but U2 C theta 2 minus U1 C theta 1 by G. Note that in this particular problem already we have discussed that flow is perfectly radial at the inlet. So, there is no swirl component of velocity at the inlet. So, this is equal to 0. Okay. So, this is C1. So, this is C1 equal to CR1, this is U1 and this is W1. So, basically we can write it U2 C theta 2 by G. So, that is the head, ideal head. We know U2, that we have already calculated. What we need to know? We need to know the swirl component of velocity at the outlet. So, from the velocity triangle and knowing the value of CR2 and U2 from the previous from this calculations, can we calculate what will be C theta 2? So, basically you can understand from the velocity triangle that C theta 2 will be equal to U2 minus W theta 2. This is very simple. Now, U 2 we know, and what about W theta 2? We know CR 2, we know beta 2. So, we can write W theta 2 in terms of known quantities, right. W theta 2 is not known explicitly, but it is not known implicitly. So, we can write it U 2 minus CR 2 cot beta 2. So, we know this is CR 2, this is beta 2. So, the W theta 2 will be CR 2 cot beta 2. So, if we now plug in the value of U 2, CR 2 and beta 2 is known, we can write it, it will be 18.25 minus 76 cube meter per second. It is very important to write unit always, though you are solving the problem accurately or you correctly, but if you forget to write the unit of the quantities, it is not expected to get full marks, because you need to write the unit, that will also an indication whether you have understood the problem or not. C theta 2 is the velocity component, unit will be meter per second. So, you have to write always, otherwise it may not be possible to get full marks. Okay. So, now we can calculate the H ideal. So, this is H ideal. Okay. We have seen that this is the actual head that will be developed by the pump, right. 2.4 plus 19 plus 68 q square plus 650 q square. So, we can write it, I mean you can understand that will be 21.4 plus 718 q square. Okay. So, we can write that 21.4 plus 718 q square, and that is very important. Again, if we go back to the problem statement, what it is written? See, 50% of the velocity head of the water leaving the impeller is converted to the pressure head. So, you can understand, if we try to go to the next slide. So, this is the amount of head that will be developed by the pump, right, and if we try to go back to the velocity triangle at the outlet, if we look at the velocity triangle at the outlet carefully, what we can see, and you can see that absolute velocity of the fluid leaving the impeller is having finite value. We have discussed the contribution of different velocity components in the context of net head that will be developed by the pump, right. So, the reduction in the relative component of velocity is nothing but the regain of the head, static head. Now, since the absolute component of velocity of the fluid leaving the impeller is having some finite value, so it is unexpected that, rather it is expected that that velocity component will be that the kinetic energy corresponding to that velocity will be converted into the pressure head while the liquid is passing through the volute casing, right. Now, so basically it is also mentioned that while the liquid is passing through the volute casing, it is not possible to convert all the kinetic energy into the equal amount of head. So, can't we write that this is nothing but U2 C theta 2 by G, okay, minus, so this is the head that we are expecting to get from the pump following the Euler equation, but this much amount of head we are not going to get. This is the head we are going to get from this pump, but we are not going to get. Reason is very simple, that is already given, that 50% of the water, 50% of the velocity head will not be converted into the pressure head while the liquid passing through the volute casing. So, this should be always less than C2 square by 2G, right. But so you can understand that this is the ideal amount, this is the ideal head that we can get, but this should be always less than by this quantity. This quantity is nothing but the loss of energy, leaving loss, that is what we have discussed in the context of two different types of blade, that is what we have, if we can recall. So, the leaving loss, that is half mc2 square, that is loss. So, that amount cannot be converted. So, if we try to recall, so u2 c theta 2 by g, that is the head that we can expect from the pump. This amount of kinetic energy will be lost, we will not be able to recover. Now, it is also given that this is not the total amount, only 50%. So, this is 0.5 into C2 square by 2g, right. Again I am telling, this is very important point to understand, that this is the actual head, this is the actual head that will be developed by the pump, right. Now, this is the head from the given configuration that the swirl is absent at the inlet. If we try to recall the Euler equation, we will be getting this is the amount of head that will be developed, but this is not the case in reality. Some amount of loss will be there, and that is because of the leaving loss. So, we can see that C2 square by 2g, that is the loss, total leaving loss, but that loss is not there, we can recover 50% of that leaving loss through the volute. So, basically this is the head, again I am telling, this is very important point to understand, this is the, this quantity dictates that the head that will be developed by the pump in ideal condition, and this quantity is the leaving loss. So, basically to arrest that loss, we need to allow water or any liquid to pass through the volute, and that is what that is the objective of having volute or casing. Now, it is given that though this is the leaving loss, but only 50% is 50% is recovered, right. If we go to the problem statement, that 50% of the velocity at water leaving the impeller is converted to the pressure head. So, that means we will be taking only 0.5 C2 square by 2g. I could have written straight away minus 0.5 C2 square by 2g, but only to make you understand that this is the leaving loss. Our objective is to recover that loss by allowing liquid to flow through a volute casing, and in the volute casing that is designed for this particular pump is that 50% will be converted to the pressure head. So, that means this 50% is lost. So, this is nothing but u2 c theta 2 by g minus 0.5 c2 square by 2g, right. So, if we do this calculation, we will be getting our equation, that is 937 q square, right. We can write all the, because we can write u2, what is u2? u2 is, so we can write 1 by 2g into 2 into u is 18.25 into 18 point c theta 2 is u2 minus w theta 2 minus 76 cube, right. So, this is c theta 2, that is what we have calculated. So, this is c theta 2 18.25 minus 76 cube. So, we are now putting the value of c theta 2 over here, that is nothing but u2 into c theta 2, and that is u2. So, I am taking 2g outside, so 2 into 2, so 1 by g, that is there, minus 0.5 into C2 square, right. What is C2 square? So, I mean 0.5 into C2 square. Again, what we can write, what is C2 square? Just try to go back to the, if we try to again look at the velocity triangle at the outlet, what about C2? C2 square is equal to CR2 square plus C theta 2 square, right. So, C2 square equal to CR2 square plus C theta 2 square. Okay. So, you can understand that 0.5 into 0.5 into, I mean if we try to write it, so we have seen that C2 square equal to CR2 square plus C theta 2 square. What is CR2 square? 18.25 square. Okay. What is CR2 square? CR2 is we have calculated, CR2 is 53.2 cube. So, we have calculated CR2 from here. So, CR2 is equal to 53.2. Okay. So, 53.2 square q square plus C theta 2 square means this square. So, basically 18.25 minus 76 cube square. Okay. So, if we compare, rather if we compare this left hand side with right hand side, we will be getting this equation, which is a quadratic equation of cube, and that is 70.66 cube minus 4.07 equal to 0. So, this is, so if we compare the LHS with the RHS of this equation, eventually we are getting a quadratic equation of cube, and if we solve it, q will be 0.03823 meter cube per second. So, this is the answer, and if you would like to convert it into liter per second, you can do it. So, basically this is the answer. So, this is the flow rate. So, one objective of this problem was to calculate the flow rate. So, we have now calculated the flow rate, and remaining task is to calculate manometric efficiency, that is again straightforward. So, you can understand that this is the flow rate. If you solve this quadratic equation, you will be getting two values of q, one may not be physically correct. So, you can try, and this is the flow rate. So, next task is to calculate manometric efficiency. Already I have written the mathematical form of this particular efficiency. So, this is H actual by H ideal. Now, let us quickly solve this or quickly calculate it. So, manometric efficiency, as I told you, this actual head will be is not equal to the ideal head. To be precise, actual head will be always less than the ideal head. So, actual head H actual is always some constant into H ideal, and this constant is eta manometric or eta hydraulic. In some books, the same efficiency as the manometric efficiency is termed as the hydraulic efficiency. So, basically you can understand this eta manometric is nothing but H actual divided by H ideal, and so you can understand that is H actual I can write divided by H ideal is equal to u2 c theta 2 by g, and we can write that is g into H actual divided by u2 c theta 2. Now, if we try to write over here that, so eta manometric equal to 9.81, that is the value of g we are taking, and what is H actual? H actual just now I have written in the previous slide, that is nothing but 21.4 plus 718 q square. By this time we have calculated the magnitude of cube that will be delivered by the pump, that is meter cube per second. So, just we can write this is the H actual. So, this is nothing but 21.4 plus 718 into what is the value of Q? 0.03823. So, 0.0283823 Q square, right. So, this is the H actual divided by, so I am writing this. So, what about H ideal? U2 C theta 2 by G, G I have already taken. So, what is U2? U2 is 18.25 and C theta 2 is U2 minus C theta 2, C theta 2 is equal to U2 minus W theta 2 and that is U2 minus CR2 cot beta 2. So, if we try to write the value of C theta 2 over here, C theta 2, somewhere we have calculated C theta 2, where is C theta 2? This is. So, that is 18.25 minus 76 into cube. So, I am writing 18.25 minus 76 into cube into 0.03823, right. So, this is again very simple, just some algebraic calculation and that is nothing but it is coming. So, this is C2 C theta 2, this is U2 and this is H actual. So, it is coming 78.5%. Okay. So, this is what we have solved today. So, now if we try to summarize what we have learned from today's class is that we have taken up a numerical problem for the radial flow pump. The problem is such that we had to draw velocity triangles, because without velocity triangles it is very difficult to solve the problem. So, again I am telling the first objective while solving any particular problem is to draw the velocity triangles both at inlet and outlet. From this particular problem we also had to recapitulate about the pumping system, suction pipe, static height in the suction line, static height in the delivery line, also the frictional losses in the suction and delivery pipe. And what is important that we also had to recall the Euler equation which is used to predict the head that will be developed by a pump, and that head is the not the actual head, rather that is the ideal head. Now, since the actual head will be supplied by the pump will be always less than that predicted by Euler equation. So, we had to also recapitulate one important efficiency in the context of pump operation is the manometric efficiency, and we have calculated the flow velocity components from the velocity triangle using the concept that we have learned from the previous classes. So, and eventually we have calculated the flow rate and efficiency. What you can see from the efficiency that we have calculated, that is 78.5. So, using this particular pump, if we install if we install this particular pump in a pumping station and using this pump we can supply water having manometric efficiency 78.5. If manometric efficiency becomes higher, then of course, you can understand what we have discussed in one of my previous classes is that the overall efficiency also will be higher. So, our objective should be to increase the overall efficiency, since overall efficiency depends on the manometric efficiency, mechanical efficiency and other efficiencies that we have discussed. So, if the manometric efficiency is at the higher side, definitely we can expect that overall efficiency also will be higher. So, with this I stop here today and we shall continue our discussion in the next class. Thank you.